Hello everyone. Today's video is about finding out the inductor, the value of inductor using an oscilloscope. So the basic idea is to use a pulse to change the LC tank circuit and find out the resonant frequency, and then by using the formula we're going to find out what is the inductance of this specific circuit. So this is the basic circuit which is being used in this experiment. I have 1 kilo ohm resistor, a supply voltage of 5 volts, and a switch that is normally turned off, and then a LC tank circuit, and which is then grounded. You can see the red lines which show where you have to connect the oscilloscope. So to charge the inductor, I'm gonna press this switch and release it after some time. Okay, but then there is a specific procedure which you need to follow to find out the proper wave. Here is a list of steps that you may want to try to find out the resonant wave. Number 1, you have to set the oscilloscopes to the defaults. The coupling should be DC, and the display should show 1 volt per division. Okay, you can first set the oscilloscope to the auto, let it find out the signal, and then you can just bring it and scale it down to show you a bigger picture of the waveform. You don't want to see any noise signals in terms of millivolts. Then there is an important thing, which is the trigger level. You have to set the trigger level from 1 volt to 3 volts if as necessary. So this is specifically important when you have a bigger inductor, like which is in terms of maybe 1 or 2 millihenries, or at least 100 microhenries, or 500 or 600 or something. Because if you have a very small inductor, then what happens is the voltage spikes are very low, and they are very close to the noise levels. So it's very difficult to find out the frequency or the trigger level for the oscilloscope. So it's more work if you have a small inductor, like in terms of 1 microhenry or 10 microhenry or something like that. So I'll show you in a moment. So third step is you have to push the button down and select the single in oscilloscope. So single trigger. So the single function in the oscilloscope will only capture a single snapshot as soon as the trigger level is touched. It will not keep on showing you multiple waveforms. Okay, so this is also important. You have to use the single function of the oscilloscope. So when the switch is pressed and you have pressed the single, you have to release the switch. So once the oscilloscope gets triggered, it will take a snapshot of that waveform. So number 4 is release the switch, and then number 5, you should now see the waveform of the LC tank circuit at the resonant frequency. Then we know the LC tank resonant frequency is shown by this formula, and if you rearrange the formula, you can find out the L, which is inductor in henries, and that's equal to 1 over 4 pi square F square into C. And now let's follow the procedure. So this specific circuit on the breadboard is very much what I just showed you on the screen. I have my oscilloscope probes connected to the 1 nanofarad capacitor, and I have 1 kilo ohm resistor. This is a push button, and I have to put the inductor in it. Okay, so, and this is the power supply, these green and red lines. So this is a 4 volt power supply coming DC. The power supply must be as clean as possible. So you may run into troubles if you have a switch mode power supply, because they itself generate lots of noise signals, especially when you're dealing with the lower voltages and higher frequencies. So the oscilloscope will obviously capture the noise signals coming from the switch mode power supply. So it's very much important that your power supply signal is clean and DC. Okay, so to be sure with the experiments, I have some inductors which are like this, and these are color coded inductors. Sorry for the lighting, but I have this one. So what happens is you have to read the color code. So if you can't see, I'll show you like this. So you have the brown, and then black, and then red. The brown is 1, black is 0, so 10, then red is a multiplier, which is 2. So 10, 0, and 2 more zeros, that's 1000 nanohenries or 1 millihenry. So I've also written the value 1 millihenry like this. So this is how you read the inductor. It's more like a capacitor, the resistor. So the first digit, then we have second digit, and then we have multiplier. X is the number here. You have it follows the same code as the resistors do. Then we have tolerance. If the third band is some gold or silver, it means the multiplier 0.1 and 0.01. Gold will be 0.1 and the silver would be 0.01. Okay, but if the gold or silver bands are here, the fourth band, then that means it's a tolerance. It's a 5% or 10% of the value. So the value can fluctuate in between those percentages. Okay, so now just let's install the inductor, 1 milliohm inductor here, and then yeah, my power supply is connected, and I press the auto, and this is the normal signal which my oscilloscope is seeing. It's in the range of millivolts, so I'll scale it down to see at least 1 to 2 volts. So this one, and with this I'll set my trigger. I'll set my trigger to 3 volts. But this can be experimented with actually, in fact. So let's start with 3 volts almost, and I'll push the switch down to charge the capacitor, and I'll also push the single. Now this is important. You can see that we have a wave here, so the oscilloscope is actually waiting for some trigger value here. So if you don't see wait and you see this stop, then it means that something is already captured by your oscilloscope. So you have to wait for this wait option here. Okay, so as soon as I release, I see a waveform, and that's what I need. Okay, so if I scale it horizontally, I can see that this is a normal waveform for the LC tank circuit. Okay, and if I go to the cursor and find out sorry, this is the scale, and find out my frequency. So yeah, the first way to find out the frequency is like through cursors, X. I'll just find a timeline in between the peak to peak like this. So yeah, it's not very accurate. I can zoom in actually to find a precise peak. Okay, like here and like here. So it shows somewhere around 68 kilohertz. Okay, so since 68 kilohertz, if you see this value, this is the difference between the x-axis values, which is the time. Ax is 5.9 microseconds. 5.9 microseconds, and then 1 over x is frequency, 1.68 kilohertz. Okay, so yeah, that's the frequency. Another way to find out the frequency is just to go to the measure and go to the horizontal, then horizontal here, and then the frequency. And the frequency it shows like 163.9. Okay, it's a bit lower than what I calculated, but to be sure you can just do it a couple of more times. So I'll do auto again, scale it down to show some volts. I have like 2.7 volts, 3 volts here. So trigger level is again to the 3 volts or something like that, and I push the button down, press single. So waiting for the signal, and then release. It didn't capture, no worries. I put this trigger down. Yeah, but I have to push this button and press the single. Yeah, this is a proper way to capture it. And if I do it again, yeah, you can see the frequency here. It's 166, 170, 169. So that's the calculation. So I'll take it like 169 kilohertz. So what we're gonna have to do with that frequency, we have to go to some online calculator to find out what's the inductance. Okay, so this is what you can find out online. Some Omni calculator shows the resonant frequency calculator. I have a capacitor of 1 nanofarad, and I found out that my frequency is 169 kilohertz. So that's 886 microhenry. That's like 0.88 millihenries. So the actual value on my inductor here that's written is 1 millihenry. Okay, so if I do 168, it's like almost 0.89 or 0.9 millihenries. So yeah, that's what you can find out from the from this resonant frequency data. Okay, so I got another tester here, which also measures the inductor. So what will happen? What will I do? I'll just put the inductor here, lock it up, and press. Okay, so it shows inductor, and that's 0.98 microhenries. That's close, very, very close to the 1 millihenry. So seems like we have got some data. Okay, so everything just so the deviation that happens in the measurement of oscilloscope is bit of stray capacitances in here, and the specifically this capacitor, this capacitor. So if this capacitor is not actually 1 nanofarad because of the tolerance and stuff like that, the value of inductor would be also affected. So the reason, and this is more accurate, is because the capacitor which is used to make a LC tank circuit, or the mechanism will have to be more precise, and surface mount, which is a lower tolerance, is like in terms of 1% or so. So this is the basic idea. You need to put a pulse through this LC tank circuit and just capture a resonant signal over there, and this is how you find out the inductance using a pulse and a oscilloscope. There's no need for any Arduino or any function generator or anything. This is the simplest way to do it. Okay, so let's try the experiment one more time with a very small inductor. because these small inductors are hardest to capture. So I have this another inductor which has a color code of brown, green, and then black. So so brown is 1, green is 5, so that's 1 5, and black means 0, so that means there are no zeros, no multipliers. Okay, so 10 raised to the power 0 is 1 into 1, so that's a 15 microhenry. So let's see how that performs in our circuit. I put in here, and yeah, I'll just press auto to let the oscilloscope capture. It's a default waveform. Now what will I do? I'll set the trigger level to somewhere around 1 volt, because this is a very tiny inductor, so I would expect very small voltage or waveform here, with a very small voltage, the waveform. Okay, so let's try from 1 volts, and I press single. I can see that I have the wait option in here, so that means that the trigger level is some level where there's no noisy spike, so that's why the oscilloscope is waiting for the wait signal. Okay, so when I press the button and I push the button, it shows nothing, so it means that the oscilloscope is not able to capture the waveform. Okay, so I bring the trigger level down to somewhere 600 millivolts and push the button. Okay, I can see a small waveform, but I think that's not good enough. So press the single again, press the button, nothing happens. Further down, press again, I can see the waveform. Again single, wait option, then press. I can see the waveform. Okay, so I think that's where my trigger signal could be. So what I'll do, I'll just press the button, the push button, and then push the single. I can see it's waiting for the signal, then I release the push button. Okay, I see the tiny signal over there. This most probably the noise signal, so no, that's not my signal, and the frequency is 147 kilohertz. Okay, so just in case it was in if it was in unknown inductor, I would do it a couple of times to verify the data. Okay, so I'll bring it down, the trigger level, I bring it down, press the button, push button again, then we'll wait for the trigger and then release. Okay, now this looks like a promising resonant waveform, and yeah, okay, there's no noise signal. This is a proper waveform. It appears to be coming from the LC tank circuit, and if I zoom in, you can see that I have a frequency measurement of 1.33 megahertz. Okay, 1.33 megahertz. So let's put it in the calculator and see what's the value of the inductor. So here's my calculator. I have 1 nanofarad capacitor, and then I have frequency which is found to be 1.33 megahertz, and that gives me a value of 4.32 microhenry, which is very close to the inductor's color code, that is 15 microhenry. Okay, so to do a further check, I'll test the inductor with my multi-tester over here. And that's it. It shows 0.2 millihenry, so that's like a 20 microhenry. So that's the 5 microhenry off. Okay, let's do it again. .2 millihenry. Okay, so the previous inductor was very much accurate, but this was is not as much accurate. This time my oscilloscope's value is more accurate, so it shows 14.32 nanohenry, a microhenry, and the color code shows 15 microhenry, and the this meter multifunction tester, it shows 20 microhenry. So that's you wanna do it a couple of times with the oscilloscope to verify the results. Okay, so that's how you do the inductor testing using a pulse and an oscilloscope.